Hello, and welcome to Photonics Next 2025 Fall Summit Session, Overcoming Design and Evaluation Challenges of Intra-pair Skew in High-Speed Interfaces, sponsored by NRZ Company. I'm Justine Murphy, Multimedia Director of Endeavor Business Media's Digital Infrastructure Group. Now, before we get started, just a bit of housekeeping. If you have any technical difficulties during the event, please enter your question in the questions window, and our technical experts will be happy to help. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. And we welcome your questions during the session. We'll answer as many of those as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. You can do that by simply typing them into the question window on the side of the screen and hitting the submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. And if you'd like to increase the size of the windows on the screen, click in the upper right corner. Also, please be aware that today's event is being recorded and you'll be notified by email when the archive is available. Lastly, at the end of the session, a screen will pop up asking you to fill out a quick survey. Please make sure to do that. It will help guide us on future content that we'll continue to provide. And now I'm happy to introduce our speaker, Hiroshi Goto, an engineer with NRZ. Hello, Hiroshi. The floor is yours.
Thank you, Chaplin. This is Mr. Goto with NRZ. Thank you very much for everyone for joining today's webinar. Today, I'm going to talk about PCIe Generation 6 link training test solutions and unique intra-pair skew resolution. Today's agenda, first, I'm going to talk about PCIe Gen 6 test solutions, overview, and also receiver link equalization training compliance test. Then, quick introduction of NRZ PCIe receiver link equalization test solutions. Then, talk about a physical layer for the error correction test solutions. Then, intra-skew test solution. And last page, very quick NRZ BAT MP1900, a quick introduction. So the key three benefits of PCIe Generation 6. First one is a double bandwidth. The last generation PCIe Gen 5, 32G gigabit per second per lane. Now it's doubled, so 64G transfer speed per lane. It's gonna be 256 gigabit byte per second for 16 lanes. That one is always double, almost every 3 years. Then low latency is the key of PCIe. Utilizing the fleet control unit with the fleets. Kind of a light effect for the error corrections, and using the PAM4, it's achieved the double bandwidth, but very low latency, still very low latency. Then the third one is a backward compatibilities. Even the PAM4 PCIe Generation 6, it's always backward compatibility for PCIe 1 to 5. Then, what's new and key for PCIe Generation 6? The first one is PAM4. For optical engineers, maybe PAM4 is nothing new, but for this PCIe interconnect for the backplane, the PAM4 is very new. Up to Generation 5, all modulation scheme was NRZ. Then Generation 6 start using PAM4 to double the bit. So the baud rate is same of 32 gigabit per second, but using PAM4, you can double the bandwidth. However, the disadvantage of PAM4 is you automatically lose 9 dB SNR. Then that low SNR affects the BER. So to compensate the BER, now the forward error correction is used. However, the PCIe use light forward error correction. So compared to the IEEE, like a Reed Solomon type, it's a very lightweight and very strong CRC. So that achieve the very low latency. So new criteria of BER or FBER and frit errors. FBER is a new concept. So successive burst errors propagating by the DFE will be counted as a one single error. So if you have like a 101010 clock pattern, then first bit fails, it automatically fails the contiguous errors so contiguous error of any numbers of contiguous error can be counted as a one error. And FBR must be better than E-6. That is the new criteria. Compared to the previous generation PCI Gen 5, the PCI generation Gen 5 use E-12, almost no errors for 2 minutes. That is a confidence level of E-12 is 95% or better. Now the generation 6 use E-6 with a CRC. So receivers link equalization training compliance test. PCI-SIG offers 4 times per year compliance workshop. You can bring your DUT to get the certification. For the receiver link equalization test procedure, first, the calibration to make a worst case scenario of receiver test. You can see very small I of generation Gen 5, that is 15 millivolt I height, and I width is 0.3 UI. Compared to the Gen 5, now Gen 6 is very, very severe. I height is only 6 millivolt because PAM4, and only 0.1 UI, 3.13 picosecond I width. It's a very small I width. Then, under this stress condition, very small I, the DUT needs to make a successful link training, then get looped back. Then once it gets looped back, now make a BER measurement. The criteria is E-6, FBER E-6 for 15 seconds. For Gen 5, again, E-12 for 125 seconds. Now, this calibration procedure is quite time consuming, it takes 3-4 hours, but now the actual test is less than 2 minutes. This table shows the stress I conditions. So launch amplitude 800 and 1 UI 31 picosecond. And you can see, the I height, I width, and RJ, DM, and CM, and SSC. The loss criteria or loss topology from chip to chip, the PCI Gen 6 specifies 32 dB loss at the worst case scenario. So a lot of ISI. Then you characterize the all channel from input to output to be 32 dB, including the package loss of the chip. Calibration is quite straightforward, but RJ calibration is now a little bit tricky because the target RJ is 250 femtosecond RMS. But now you can see, as you can see, now the intrinsic jitter of the test equipment, scope intrinsic jitter, and also BAT pulse pattern generators intrinsic jitter is almost like a 200 femtosecond RMS. So if your target is 250, you cannot use this portion. And now scope may need a noise removal to compensate the intrinsic jitter of the scope itself. So now you have to use this linear portion. If you use this kind of portion, you cannot make a linear fitting. So this one is a measurement example of RJ calibration. So, and it's used this portion to get the target 250 femtosecond RMS. And RJ is also very tricky because for different descriptions, UI peak to peak, picosecond peak to peak, then UI RMS and picosecond RMS. So, and this BAT has a function to convert, for example, this one, 0.112 UI peak to peak. It is converted like 0.248 picosecond. That is 250 femtosecond RMS. Then let me talk about the receiver link training test solutions. This block diagram is a very typical compliance test pulse pattern generator of BAT generate a pulse pattern, compliance pattern, modified compliance pattern, and it goes to the ISI, then go to the CLB compliance load board, and the DUT is on this board. So signal goes through the chem connector and loop back, and coming back through the chem connector, go back to the error detector. And this error detector has everything to measure the PER, clock data recovery embedded. Also, the pulse pattern generator side, we have everything to embed all impairment like SJ, RJ, and SSC. As I said, the calibration is the most important to achieve the stressed eye. And then, and it is a partner with Tektronix and LEQ. So LEQ and Tektronix provide automated calibration software. And also, and it's but work with Keysight real-time scope. So all three major vendor of real-time scope can be used with its parts. This is an example of the LTSSM through generation 1 to generation 6. You can see what's going on with the training sequence. Then BAT has a function to analyze each step of link training, and you can manipulate the timeout second from the table. This is an example of the receiver test. So now receiver pass of E-12, then you can make a jitter tolerance test. The red line is the compliance mask, and you can measure how much the margin you have from the mask or specifications. This is another example of the jitter tolerance. Now, the PCI Gen 6 use FPER. So now you can see blue line is a PAM4 symbol error, and yellow is FPER. Then fleet error rate, so correctable and uncorrectable error, and increasing sinusoidal jitter of 100 megahertz up to 80 milli UI, all error is correctable. But when you inject 0.1 UI, 100 milli UI, SJ, now you start seeing some fleet errors. So that is uncorrectable error. But still, that is still E-6, so still okay. From the PPG side, once you get a DUT pass of the compliance test, you can change the preset or cursor of the pulse pattern generator to find, if the DUT may have a better preset or cursor of preset or equalization. So now for the error collection for physical layer. Once everything is embedded in the networks, network has a function to coding and decoding and for the error collection. So now you do not have to worry about the, FEC is broken or still everything is fine, no error after for the error collection. However, when you characterize the chip or device such as like a SADS, clock data recovery, DFB, total loss, optical. They may not have a decoding function of forward error correction, but still you need to test if the errors can be corrected or not corrected. How can you do that? And its part has a function to analyze the errors, and it can make a judgment that the errors can be corrected or not corrected by forward error correction. That function can be used for flipped forward error correction or Reed-Solomon forward error corrections. So always needs to make a loop back. So PPG generate a stress signal, then loop back and coming back to the error detector. So and this error detector has the function to measure PAM4 symbol errors. First BER, FBER, and low BER. Then the error detector has a function to analyze that error can be corrected or not corrected. Now you can see flit error is 0, which means all errors can be corrected. And also error detector has a function to show, up to 3 flit errors can be corrected, but 4 or more uncorrectable. So it's a red. And this kind of bar graph shows you what for your analysis. Then error detector has a very detect analysis, which transit bit of PAM4. PAM4 has a 12 different transit, and you can find which transit has errors. Then again, as I said, this kind of bar graph or histogram of correctable and uncorrectable errors. This is just an example when you inject no SJ, all errors. No, actually no errors. Now start injecting SJ, start seeing some errors, but still correctable. Then inject a lot of SJ, now fake is broken and not correctable errors. So now the next topic is intra-pair skew test solution. So PCI Gen 6, only 32 picosecond unit interval. But firstly, let me explain what's the intra-pair skew. The intra-pair skew is the time difference between positive and negative differential transmissions. Without any intra-pair skew, positive and negative completely phase match. But for some reasons, if you have some skew between positive and negative, that's going to be a problem, especially for the very high speed transmission like PCI Gen 6 or PCI Gen 7 or IEEE 100G, 200G. So the PCI Gen 6, one UI or one unit interval is only 31 picosecond. That is only 5 millimeter difference of the PCB strip line, or 7.2 millimeter for the cable. So which means if you have 1 millimeter difference of the cable between positive and negative, now that means 5 picosecond skew mismatch. That is almost 1/6. So that is almost 18%, 19%. You will lose the phase match, only 1 millimeter difference, and 7 millimeter difference, you completely miss one UI. And then now, few millimeter skew can cause a bit errors. Then it causes a bit error rate, or you lose a skew margin of your DUTs. Now, this is a simulation of a skew between positive and negative. When you have no skew between positive and negative NRZ. Now differential signal is very clean. But you have 0.3 UI now, some distortion. Then 0.6 UI, huge distortion. However, for NRZ, still the decision point is the center of the eye. Now, maybe this kind of distortion may not affect the BER so much. However, for the PAM4, now the top eye and bottom eye, phase margin is very, very small, mainly because of the TRTF. So TRTF, rising edge and falling edge, it's, ideally it's rectangle, but actually it's not, because of the speed of the chip. So now this 0 to 3 TRTF always eat the phase margin of the top and bottom eye. Then if you have a skew, that eats the phase margin of the top and bottom eye. This is the very interesting data of the actual measurement. Now, give a skew between P and N through the differential trace, pair trace. Blue trace is the input of the trace. Then green trace is output of the differential pair trace. When you have no skew, input, output, of course, only the ISI channel loss only, so you can see very smooth trace. Now, increasing the skew between P and N, now you start seeing the degradation of the frequency domain. Maybe 200 milli not so much, but now 300 milli negative, you see big dip, and 500 you have a lot of dip. When you give a 500 milli skew, now at the Nyquist frequency, you have 8 dB additional loss compared to the 0 UI skew, which means you will lose 8 dB, Nyquist frequency, which means the fundamental signal component. So you will lose a lot of energy of the signal. Now, this is the time domain. This is a frequency domain, and this is a time domain. Again, you can see input of the trace and output of the trace. Now, 0 milli skew completely matched. To see the skew visually, clearly, now scope has a function to invert the positive signal. So now you can see completely overlapped. Then give a skew 300 or 600 milli. The input is just you can see the skew, so skew mismatch. But output of the differential trace, now the signal is very degraded or distorted, and it affects the BER significantly. Now, how do you make a repeatable and accurate skew tolerance measurement? Historically, this kind of trombone type mechanical skew is used, but the linearity is not so great, repeatability is not so great, granularity is not so great. Now, and it's use the 2 pulse pattern generators, and you can completely clock sync and pattern sync, and you can give a 2 milli skew resolution up to plus minus 550 milli, so which covers 1 UI. The important thing to start the measurement, you need to make a calibration. As I said, scope has a function to invert the signal. So invert data bar signal and adjust the skew of the PPG to get completely matched on the screen. You need to make this kind of a magnified. Then make sure the pattern completely matched of P and N. Again, N is inverted on the screen, but actually this is a P and N differential data. Then this is a test example of using the real DUT of PCI-Gen 6 root complex through the 30 dB total loss, and but generate a signal and go to the receiver of the device under the test, DUT loop back the signal and go back to the error detector. Now, input signal, you can just see the skew, but again, you can see distorted signal. And this is the I of the PAM4. So positive and negative and differential. So when you give a 300 milli skew, still I is open, but compared to the 0 milli I of top I, bottom I is smaller, and 600 milli no more eyes. So using this, we measured the skew tolerance of the DUT PCI-Gen 6 root complex. So at 0 milli skew, E-8 or something, and plus minus 100 milli, almost no difference of the BER. But when you give plus minus 200 milli, you start seeing the degradation of the BER. And then 300, you will get like a 1 decade degradation of the BER. So 300 is maybe the maximum you have on your trace. In this case, no crosstalk, no DMI, CMI, no jitter, no SSC. Then start injecting the SJ. So this is the starting point. No SJ. Start SJ 24 milli, 36 milli, and 40 milli, 48 milli. Now the spec is better than E-6. So still this DUT has some margin, but the nominal of SJ for compliance test is 48 milli. So now still this DUT can pass the compliance test. Then DMI inject 5 milli DM differential mode interference. Now you will lose almost 1 decade BER. Okay, so this is the last slide. So MP1900, just let me make a quick introduction of ANRIZ 1900. It's a multi-channel PAM4 NRZ part up to 128 gigabit per second per lens. And you can configure max 16 lens 32G NRZ or quad channel PAM4. And you can make a clock sync and pattern sync. Signal integrity, very low intrinsic jitter, and very fast TRTF. For tap emphasis, completely independent, plus minus 20 dB emphasis functions. Error detector has embedded clock data recovery. You can inject 2 tones of SJ, RJ, random jitter, BUJ for crosstalk simulation, period jitter, SSC, noise, CMI, DMI, and broadband white noise. And these are the major applications. And thank you very much for being patient with my English. This is the last slide. Thank you very much.
Great. That was fantastic. Thank you so much. And that concludes this Photonics Next session. I'm afraid we won't have time for questions, but Hiroshi will address those later offline. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Hiroshi Goto for a great presentation, and NRZ Company for sponsoring this session, and of course, all of you too for joining us. And once again, please do fill out that survey that will pop up once we're done here. We appreciate your time filling out that quick survey, as it will help provide guidance on future content we'll continue to provide. Have a great day.